So you might be wondering, well, Andrew, didn't we just talk about application security? Why do we keep focusing on this, and why do we keep talking about web applications now? Aren't they pretty much the same? I mean, aren't they still applications? Well, they are, but they have also become a very specific type of application because they're so flexible nowadays. Just think about how much stuff you can do today with just your browser. You can check your email, you can visit websites, you can send files, receive files, you can connect over remote desktop, you can even play games, just to mention a few. Basically, you can just live your life in front of a computer just inside of a browser. Which means that whatever applications your browser ends up connecting to in the backend, well, those are the web applications that can deliver pretty much any service to us nowadays. Not to mention the cloud environments and cloud applications and cloud services. That's basically everything that you can do with a computer has slowly and steadily become accessible through a browser. And while web applications are still based on the same basic principles like the HTTP protocol and a web browser, well, this kind of huge flexibility that we are seeing nowadays has made them an extremely tasty target for attackers. And another reason why web applications are special is that they are designed to be exposed. I mean, you are hosting a website, you're developing a new service, you want people to use it, so you make it publicly available over the internet. And that's, from the very beginning, a huge risk. Also remember that a web application can be accessed through a client. So basically we have 2 points of contact here and 2 potential places where vulnerabilities can be found. That is your client, your browser. So an attacker might be targeting the client that you're using to access an application, or the application hosting system itself, like the server that is hosting the application, the cloud service that is hosting it, the application that is delivering those web pages to you. And in the web world, everything revolves around the URLs, Uniform Resource Locators. Now, these are just strings that are made up of a couple of components here. And in general, we think of an URL as a method for us to tell the web server that we intend to request a specific resource that is hosted by that web server. And that's perhaps true in 90 or 90+% of all cases. But the URL can also be used to encode additional information that is being sent to the web server itself, which makes URLs a vector for potential attacks. And if you think about it, a URL that is received by a web server is still some sort of an input. And we come back to that discussion about input validation. What exactly are you expecting to receive from your clients? Are you sure that your clients are always going to request valid resources and they're going to request them correctly according to the HTTP standards and obeying all the protocols involved? Or at some point, you might have to actually analyze the URLs received from your clients and figure out whether inside of that URL isn't a hidden script, like a script that is encoded using percent encoding. We're going to talk about this in a couple of slides. Or you might even find another domain inside of that URL that is hidden behind a redirect or behind a small piece of JavaScript code that is also encoding and obfuscated within the same URL. So don't just think that a URL is some sort of a completely malicious-free piece of code, because it can actually be interpreted and it can end up having executable code in it. So speaking of percent encoding and decoding, this is a technique that is available by default in pretty much any web browser out there. And it's a technique that can also be interpreted by the web servers. It's not malicious by its definition. It's actually a way to encode additional information inside of a URL, because a URL by definition is only allowed to store ASCII characters and a couple of reserved characters that are used as delimiters. And usually these are used to encode additional information or to separate specific parts of the URL. Other than that, though, the URL cannot hold any other types of characters. So if you are planning on embedding some sort of a scripting information or another URL perhaps encoded in another URL, then you will be forced to re-encode those special characters using a special syntax, a special notation or conversion table called the percent encoding table. And percent encoding, again, it's not any kind of secret. It's basically called percent encoding because the notation that is being used inside of a URL to display those unprintable or reserved characters relies on the fact that they all start with the percent sign. So for example, if I were to re-encode a slash inside of my URL, right, I could use the %2f character code. And the browser as well as the web server are going to be able to decode this notation and understand that there is a slash sign symbol in there. But percent encoding is not designed to be used only with printable characters. So we could even encode binary data inside of those, because binary data basically means that we're going to just split the entire binary chunk of code that we might have into, well, bytes, okay? And each byte can be displayed by using 2 hexadecimal symbols. So we could, for example, get a byte value that is 0f right here, and we can represent it with a percent sign in front of it as %0f. This is going to range from %00 up to %ff, which is basically able to represent all the 256 possible combinations that can occur in any byte. And since you can now represent any byte, you can now represent any string of bytes. There you go, you can now encode pure binary data into a simple printable URL. If you want to play with this, just Google percent encoding or percent encoding online or URL encoding. By the way, that's also another name for percent encoding. You're going to find a lot of tools out there and you can play with those. One screenshot here on the screen is one of those tools that I've just stumbled upon in a simple Google search. Notice that the normal text still appears printable, just like you would expect it to appear, except that all the special characters, like the less than and greater than, or the parentheses, all the symbols here that might have something to do with actual code, it might be JavaScript code, it might be an SQL query, for example, those need to be percent encoded. Now, why is this relevant? It's relevant because percent encoding can be used as a form of obfuscation, that is, hiding information within a URL. So if you are planning on validating your input, one important step here would be to prepare some sort of a decoded version of that URL, and then make sure that inside of that URL, you're not going to find any JavaScript, you're not going to find any attempts at SQL injection, or any other bogus stuff in there that might not look like legitimate use of your web application. Now, attackers are smart, there's no doubt about that. So considering that you are somehow obligated to perform this URL decoding before you can even analyze that input, well, there are attacks aimed at the decoding process itself. So an attacker could potentially craft an URL that can be expanded over and over and over up to something close to infinity, which is going to eat up the memory of the parser or of the web server that is trying to decode it. So we could have recursive decoding inside of an encoded URL, which can also lead to potential denial of service attacks. Or even buffer overflow attacks if you think about the fact that, well, that URL is probably going to be held in memory somewhere, and if you manage to expand it to a huge size, you might run out of buffer space. Of course, APIs, application programming interfaces, can be vulnerable just like any other web application. Actually, sometimes they're even more vulnerable because they're designed to be interacted in a programmatic way. So there isn't really that much complexity in the authentication part for some APIs. Most of them rely on a simple token that is being presented by anybody who has that token, and any request that comes in, as long as it has the right token, it might be stolen, it might be compromised, it might be hijacked from another session, the API doesn't care, and it's still going to accept it, and it's going to process those requests. So APIs, on the other hand, are a bit more vulnerable, I would say, than normal web applications, even though they're not as flexible. But also, one major drawback of APIs is that most of them don't really perform any kind of input validation, because we expect all the requests that come in to play by the rules, right? To obey the API rules, since they are generated by an automated tool, by a script, by a machine. Well, what if they are generated by a hacker's machine or by a malicious user? Well, APIs usually need a lot more protection here because many APIs actually perform very complex operations and allow you to change data and to interact with data as long as you have the right credentials. And we still find here the same problem with too much information in error messages. You might think that, well, since we are using an API to programmatically interact with an application, let's get as much information as we can whenever something goes bad so we can know how to fix it. Well, again, we've talked about this. Don't give too much information in your error messages because that's information that can help a potential attacker. An attacker can even cause your application to reach an error state just to see how it reacts and what kind of error messages it generates. And finally, since an API is designed to be programmatically interacted with through a script or another application, we can expect that the API usage is going to spike from time to time, because while a normal user is only able to click a few times per second perhaps in a web application, well, an API might actually receive tens or thousands or millions of requests per second because they are all automatically generated. So most APIs out there, especially those that are publicly facing over the internet, have some sort of rate limiting enabled. That is, they're only going to allow a specific number of requests in a specific amount of time, perhaps from one specific source or IP address. That is to try to throttle down the level of usage of the API itself to avoid denial of service attacks. You're probably recognizing these ideas here on the slide because we did talk about them previously when we talked about the HTTP protocol. We said that there's no state information in HTTP, even though we're using HTTP to connect to web applications that store somehow the state of our session. They know about us, they know about our user profile, they know about our previous interaction with that application. And that is being performed by using HTTP cookies. So cookies are the element, the entity that is kind of connects one request to another so that the application knows that both requests have come from the same person who might or might not be already authenticated. So session data becomes kind of similar to a secret key. If you have the right session cookie and you are able to present it to the web application is not going to ask any further questions. Is not going to ask you for your password again, it's not going to ask any questions, it's simply going to accept it as being part of a pre-existing session. And if an attacker manages to steal your session cookie, well, then the attacker is going to be able to impersonate you in that web app and send requests to that web app in your name. This is what happens many times when you see someone in your friend list on Facebook Messenger, on WhatsApp, or whatever messaging platform you're using, that they suddenly start sending spam messages to their entire address book. What they did 99% of the time was click a link that was able to execute some sort of a script on their own mobile phone, and that script was able to access the session cookie because they were already authenticated in a specific social media application. And based on that session cookie, then the application, the malicious code, was able to start sending those spam messages in their name. So that's a replay attack. So the definition of a replay attack becomes the attempt of an attacker to either sniff or intercept that session cookie or even guess it. That's right, sometimes session cookies, since they actually work as passwords, they're badly generated. Sometimes they're generated based on the current timestamp of the system, which is bad because anybody could just guess what your session is going to be the moment you click login. All right? And you don't want an attacker to be able to guess that. So it all comes down to compromising the client side of the communication, because that's that side that holds that session cookie. So if you're planning on stealing somebody's session cookie, you have a number of ways of taking over that user's session. You could perform some man-in-the-middle attack, right? Intercept the data, perform sniffing if you're over wireless, perhaps if the network is unencrypted, and you are going to see inside of that web traffic, as the web traffic is not encrypted, of course, you're going to see that session information. And from now on, of course, you could just start using it as your own. You could even compromise a browser, right? A browser is just an application that can be exploited or can be compromised by malware. Once the malware has compromised the browser, it can read the browser's memory, and somewhere in that memory or in the browser's cache even, those session cookies are going to be found. Predictable session IDs, just like we talked before, are situations in which those sessions are badly generated and the attacker doesn't even have to steal it. It can simply try and generate it again or guess it based on the fact that it knows how those session numbers were generated. And bad application programming, that might be simply errors in the code or situations that weren't accounted for during the application development. For example, imagine a situation where you're actively generating an error from the web app and the web app starts dumping session information simply because it was part of the debugging process that was at some point enabled during the application development. All right, so let's see a couple of traditional attacks on web applications. First one is cross-site request forgery, CSRF or XSRF. This one assumes that the victim that we're planning on attacking already has an authenticated and valid session with a valid website, such as a banking website. Now, the attacker, on the other hand, you can see it right here on the left, it also has a website. And that attacker assumes that the victim's browser is already logged into bank.com. So for this attack to happen, we must first either assume or trick the victim into logging in properly into a valid website. Then the victim is supposed to visit one of the hacker's owned websites. It could be a link in a spam message, it could be a link in a social media or an instant message. It's enough for the victim to just click that link. Now, that link might load a page which has some CSRF code embedded in it. It is now executed by the victim's browser. In this situation here, this is an example of a code that supposedly creates a new transaction, right? With a specific value as a destination and a specific numerical value as the amount to be transferred. This code right here is completely invisible for the user. So it's part of the web page that the user visits, and that web page belongs to the attacker. Now, when the browser sees the submit JavaScript function in here, it's going to attempt to submit it. So it's going to attempt to submit it to a real banking website with the dollar amount that was supposed to be transferred into the attacker's account, and then it's going to execute this code based on the already authenticated session that is already available within the victim's browser. So what happens here is that the banking website sees a request coming in from a valid browser, from a valid user, an authenticated user, except that the user has no idea that they performed an additional action in the background, that they just sent a request to the bank, because that request was embedded in the web page, in the malicious web page that they just visited. All right, so how do you mitigate this? Well, if the only thing that you can do is to interact with the client browser, unfortunately, there isn't much you can do about this. As long as the web application doesn't have any kind of security mechanisms built into it in order to avoid situations such as this, it has no way of knowing whether that request that it just received came from a legitimate source or from a user who was tricked into sending that legitimate request. So unfortunately, there's not much you can do on the client side. Now, on the web application side, fortunately, things are a bit brighter, but they all require the intervention of the web app developer to update the application in order to provide these security mechanisms. One security mechanism is actually called a CSRF token, or better said, an anti-CSRF token. It's just a numerical value that is hidden into every web page that is presented to the user, so that when the user actually clicks a valid link on that web page, think of your banking website, right? You just navigate all over the menu in there. You look at your expenses, you look at your credit cards, your loans, whatever you have in there. But on every click that happens on that website, there is a hidden form on that website with a hidden value that is being sent back and forth between the client and the server. This means that if a request comes in that wasn't generated by you, by your browser, by clicking on something on that actual open page, that secret number is not going to be present in that request. So if the CSRF token is missing, then the request is not going to be accepted. This is what happens in those websites that don't allow you to use the back functionality. Because when you use the back functionality, you're basically reloading a previous version of the page, which has an now invalid CSRF token. That's why many websites tell you don't use the back button. Don't use the back button because it's going to break your navigation. That's one of the reasons for not being able to click back. Now, don't send these CSRF tokens using cookies because, well, cookies are automatically embedded in those requests, and basically you're circumventing the entire protection mechanism here, because those cookies are still going to be read even if that request comes in from an illegitimate source, right? From a user clicking a link on a completely different website. You could also have some additional tricks here up your sleeve. For example, something called a double submit cookie, where you're sending the same value through a cookie and through a hidden requested field in the website. Those two values must match in order for the request to be considered valid. Of course, if the request comes in from a different web page, they're going to be missing either one of those two values. You could also look at some headers. For example, the domain or origin or refer header. These can be checked to see if the originating website matches the request that it was sent from. So this is one way of determining whether the request came in from a different website than the one it was supposed to be coming from. So if you are clicking on your execute transaction button in your banking website, well, the request itself should come from the banking website. So you should be on the banking website when you click that button, not on some other website. Of these, the origin and the refer are considered to be safer because internally and programmatically, they cannot be modified using JavaScript. Another method is by enabling the same site cookie attribute in the HTTP response header. The same site cookie attribute says whether to send the cookie along with a cross-site request or not. It has three possible values. For example, lax or relaxed when cookies are not sent on normal cross-site requests. So normally they're not sent whenever you're clicking on a different website, but they are sent whenever the user is navigating to the origin site. So when you're clicking a link that actually points to the real banking website, then the cookie is going to be attached. Now, strict means that cookies will only be sent in a first-party context. They will not be sent along with requests initiated by third-party websites. This is probably what you're looking for if you're planning on strictly protecting against cross-site request forgeries. And none, of course, cookies will be sent in all contexts, including first-party and cross-site requests. So careful with this one. Also, by the way, remember that same site can only be enabled in secure context, that is over HTTPS. Which is kind of a good thing, right? It makes people think about securing their connections more. And don't forget about more basic verification mechanisms, such as CAPTCHAs. Choose a couple of pictures in there, slide a piece of puzzle, or do something that proves that you're not a robot. Not just you're not a robot, but that you have actually performed that action in a valid context, as in the actual target website, not on some attacker's website. Even though it might be not enough against CSRF, protecting your cookies is still always a good idea. For example, securing your cookies so they're never sent over pure HTTP, or ensuring that with HTTP only, those cookies are only going to be accessed by the actual HTTP requests being sent, not by JavaScript or any other tool out there. Set an expiration date for those cookies so that a session is not going to be available forever or for, I don't know, a number of months or years. Make sure that periodically you require a re-authentication of that user just to clear everything up and to make sure that those old session tokens cannot be reused anymore. Clickjacking is another very simple type of attack, but very dangerous one. Clickjacking relies on the fact that on a normal website that has some input, perhaps login forms, with sufficient privileges, or by compromising the browser, or by making the user click on some foreign link, through JavaScript, you can change the code of that page. And by changing the code of that page, you can actually add a hidden frame on top of it. That hidden frame might have some hidden input fields, which precisely positioned on top of the real input fields on your actual login page are going to make you think that you're actually inputting your username and the password into the valid website, when in fact you are entering them into a hidden form on top of it, where the submit button is going to send them not to Netflix, but to the attacker's website. So that's clickjacking, stealing a user's input. It can be done for input fields like text fields, or it can also be done for mouse clicks as well. And a couple of the traditional methods for avoiding the risk of clickjacking is first one called frame busting. That is making sure that there is no inline frame overlaid on top of my legitimate website. Or in other words, making sure that if the top frame is not the current frame, then my frame, the one that actually holds my website, is being moved on top, right? So there's nothing else on top of it that might grab the input from my users. And you can also rely on some HTTP header settings, for example, the X-frame options inside of the HTTP header, which allows you to set a couple of attributes in here. For example, deny prevents any site from framing content. So you're basically denying the ability of the website to initialize or display any other inline frames. Same origin is going to prevent other sites, or it's going to prevent the display of frames coming in from other locations, but it's still going to allow frames that have a source code that is stored at the same location as your main website, mainly making it one of your legitimate inline frames. And finally, allow from is going to permit framing only from certain pages or certain locations. You might need them, for example, for additional functionality in your browser. You might have some sort of a chat bot, for example, that pops up in one corner to help your customers. That might be a legitimate frame that can be allowed from a specific location. Now, cross-site scripting is also one of the most common web application attacks out there, and it's basically a way to trick a user's browser into executing some piece of code whenever they visit a specific URL. As we all know, web pages are full of JavaScript code, they're full of code to be executed by the browser. Well, what if part of that web page that we're visiting includes some code uploaded by some attacker in there? It might be inside of a public comment on a commercial product. Instead of a simple comment or instead of a simple review, that review actually contains some embedded JavaScript in there. Well, guess what? Whoever visits that page and displays that review page is going to automatically have its browser execute that hidden piece of JavaScript code. That's cross-site scripting. We actually have two types of cross-site scripting. We call them reflected and stored. Reflected is when the actual link that the victim is clicking on is embedding the necessary JavaScript code that is going to be executed on their machine, on their browser. So the additional piece of code is actually sent along with the actual URL. Stored cross-site scripting is a bit more easier to understand because it's part of the web application's database, backend database. Just like in the example we said before, right? If an attacker submits a comment on a forum, and as part of the comment, they hide a piece of JavaScript code in there, and the forum application is not smart enough to sanitize that input and store that JavaScript code right in the database with all the rest of the comments, and then display it to any subsequent user who happens to visit that same page. That's an example of stored cross-site scripting. A couple of mitigation methods against this, you can probably guess them, right? First of all, sanitize your input. Don't allow anything that looks like code, JavaScript code, SQL code. Don't allow that. Identify them by their special characters perhaps, but don't allow any type of code or any type of obfuscated code to be received and stored in the requests that are coming in from your users. Also, you could have dedicated appliances that look for attacks such as cross-site scripting. We have something called a web application firewall, or WAF, which is basically just a layer 7 firewall that is specifically designed to look for HTTP requests coming in to your web servers. So it's designed to protect your web servers. It's a firewall for your web farm. Now it's going to look into all of these requests that come in, and it's going to see whether any of them match a known signature that looks like a cross-site scripting attempt. An IDS and an IPS can also do that, especially if they have layer 7 analysis abilities. They're going to have to dissect the request that's coming in from your clients and figure out whether there's something dangerous in there. Of course, don't forget to update your web applications, your web servers, because many of them have built-in protection against these types of attacks. Let me show you a couple of examples here of both reflected and stored cross-site scripting. I'm going to be using a very vulnerable web application, actually called the Damn Vulnerable Web Application. There you go. It's freely available on the internet. You can download it as a virtual machine or as a container. I really like to run it as container because it's really lightweight and allows me to fire it up really quickly. But coming back here under the cross-site scripting reflected type of an attack, we can see a very simple input field in here. What's your name? So for example, if I were to just write something here, my name is Andrei, so hello Andrei, that's it. It takes whatever I happen to input here and display it right below with a hello in front of it. Now, reflected cross-site scripting means that I might be able to add something in here that looks like a script. So let's say that instead of my name, I add a small piece of JavaScript code here that says an alert of hacked, right? and then I end up the script. This is valid JavaScript syntax right here. Now, if I click submit, I'm going to execute that piece of code, and I'm going to receive the message that says hacked. But notice what happened with the actual URL. I'm going to copy this and drag it into a notepad right here so it becomes more visible. There you go. So I'm still on the same website under the vulnerabilities, cross-site scripting reflected, and for the name, notice here there's a question mark that says name equals, and here comes the percent encoding of my script. So I basically percent encoded a JavaScript code in here, and whoever happens now to click on this link, I might embed it into a web page, I might send it over instant messaging, I might send it over email. It's enough for me to just trick somebody into clicking this link, because when they do, that code is automatically executed on their own machine. And potentially it's not just going to display a message here, but it's actually going to compromise their browser or their machine entirely. So that's reflected cross-site scripting. Next, stored cross-site scripting works pretty much the same. And you can see here we have a name and a message field. It's kind of a guest book or a review page. So I'm going to add on my name in here and just say this is a great product. All right. So I'm going to sign this guest book here. And you can see that my message is now appended to the rest of the other messages. All right. Let's pretend that now I am an attacker. So attacker is my name, and the message is going to be the same one. There you go. Same script with alert. This time I'm going to sign this guest book here. I'm still displaying this message. You're going to see in a moment why. And you can see that my contents are now added to this page. And whoever now happens to visit this page, let's see if I refresh it, if I just refresh it, there you go. It's automatically going to execute this code because it's part of the comments that are already displayed to whoever happens to visit this page. There we go. It's actually it actually appeared 2 times here because I've resent the actual message from before. So now I have 2 attack messages in the same guest book. So there you go. This is store cross-site scripting. And another well-known attack is called SQL injection, structured query language injection. This is all about attempting to inject foreign SQL statements into the application's code. This is possible, or might be possible sometimes, because whatever you're sending as an input field, at some point it ends up being part of an SQL query. So for example, in a login page, you input your username and the password. So a database of users and passwords might be somewhere located in some SQL engine in the backend, and there might be a query in the code that looks like select star from users where username equals whatever I happened to input in my web form. Now, normally, if I were just to input Andrew in there, it would check whether the username Andrew exists in the database, and then will take any actions based on that result. Now, the problem here is that by doing this simple text replacement operation, I'm just taking the text from my input field and placing it inside of my SQL query, I could potentially, if I'm using some specialized SQL characters, I could potentially break that SQL query. Not only break it, but also make it do whatever I want. Let me show you an example how this works. I'm going to come back here to our DVVA machine, and notice that for SQL injection, we have a simple input field here that expects a user ID from us. That's just going to be a numerical ID. So if I enter 1 in here and click submit, I'm going to see that my first username here defined is admin with a surname of admin. For number 2, it's going to be Gordon Brown. For number 3, it's going to be somebody else. It doesn't really matter. What I'm trying to do here is to trick this application into displaying more users than it was designed to. Now, what I can do here, I'm going to show you exactly why this works, is to write something like this. Let's say that user ID is X. I don't care about the user ID. I'm going to close here a set of quotation marks and I'm going to say or 1 equals 1. Notice that I'm missing the last quote in here. I'm going to click submit, and here's what happens. And also let me show you why this works. Let me grab this one again and look at the source of the page. That's the PHP source of this web page. Let's expand this for just a bit. You can see the check database right here has a query that says select first name and last name from users, where user ID is the input that I've provided in the numerical field. Let's grab this query and analyze it for a bit. So there you go. Select first name, last name from users, where user ID is some sort of a variable. So instead of this ID here, this is where my 1, 2, or 3 inputs would end up. And this would make this query a valid one. All right, also have a colon here at the end. Now in our previous example, this is what I've provided as an input. So let's paste this one here as well. So basically, instead of this 1, 2, or 3 here, if I were to enter this input, just look at how this expression looks like now. So select all the first name and last name from users where the user ID is something, I don't even care if this one is a valid user ID, or something that is already true and always true. And 1 equals 1 is always going to be true, right? Also notice this is why I had to skip the last quotation mark, because I already had a quotation mark from within the actual the original select statement. And I also have the ending semicolon also part of the original select statement. So when this gets executed by my web application, it's simply going to dump all the users in its database. So that's SQL injection here. I could also do some more in here, not just display information from a database, but for example, I could also extract some information pertaining to the actual system that the database is running on. So instead of just displaying an X or 1 equals 1, which I know it's always going to be true, so I could be doing something like this. I'm still going to start with an X here. I don't care about this one, or something that is always true. And then union select, I'm going to perform a union operation between the previous set of results and the new set of results, which is made up of a null field and the user function. User function is going to determine the current user that is being that's logged in and that is being used by the database. So there you go. The database is running with root privileges. Very bad. Even better, I could go one level higher and determine all the tables in the database. So right now I have another 1 equals 1 union select with null and then table name from information schema.tables. There you go. I'm gonna end the query right there. And there you go. This is the list of all the tables in my database. There you go. Obviously, you can guess that these types of queries or statements can also be used to alter the database, making changes in the database that are not normally allowed for regular users. And since I don't think there is any mention of SQL injection in any training out there without mentioning this little comic from XKCD, I'm going to leave you for a couple of seconds to read this and understand why SQL injection is a problem that really should be mitigated before it's too late. LDAP injection, a directory database this time, but still a database and still accessed using some sort of a query language, is also a possible exploit technique. Not so often used, but much more dangerous because it not only gives you access to the inner workings of a web application, but this time might actually allow an attacker to compromise the entire database of users defined in a domain directory. That's possible because LDAP queries are made up of name and value attribute pairs, and they're going to look something like this. They're separated by parentheses, by the way. So whenever we're checking for a username and the password, we might be having something such as username equals Bob, and the password equals something that was provided by Bob. Well, unfortunately, if somebody manages to enter, instead of Bob, something like this, take a moment to analyze this. Then this query here, let me just copy it one more time at the bottom, and then replace whatever comes instead of Bob with this field. There you go. Notice that right after this parenthesis in here, which matches the first one, this is basically a full and complete query, which means that whatever follows after is going to be completely ignored. So what does this query do now? Well, it checks whether the username is Bob, and that's it. This is basically a bypass for the checking of the password. This is a type of LDAP injection attack. XML attacks are possible as well. You might be wondering, how could you possibly attack something over XML? It's just text, right? Well, it actually has a couple of additional functionalities, and with more features, here comes more trouble, of course. The attack is actually called the Billion Laughs attack. And it's a type of denial of service attack, which is aimed at parsers of XML documents. So we're aiming at submitting an XML document that is going to break the entity that is supposed to read it, to interpret it. And sometimes it's called an exponential entity expansion attack. Now, if this doesn't tell you anything, let me show you an example. So that's a code example right here, and you can see that it says billion laughs attack because sometimes it is used with the LOL string. And it's based on the fact that the XML standard allows you to define your own entities. Notice here, we have an entity lol, right? This is the first one right here. And then we have an entity called lol1, which is made up of 10 lol entities, an entity lol2, which is made up of 10 lol1 entities. You can see where this is going, 3, 4, 5, 6, 7, 8, 9. And there you go. At some point, this grows exponentially. And when a parser tries to expand this and represent it in memory, most likely it's going to eat up all its memory, it's going to cause a buffer overflow, it's going to crash the application, and that's why it's called an XML bomb sometimes. Notice here, after all the entity expansions have been processed, even though this is just a very small block of XML, less than 1 kilobyte, this is going to expand to 10 to the power of 9, a billion lols, taking up almost 3 gigabytes of memory. So that's an XML bomb. That's a billion laughs attack, and it can be conducted over XML. Another attack based on XML is called the XML external entities attack or vulnerability. It's basically an ability of XML to load external files on the same machine where the file is running. And you probably can guess that this is asking for trouble. So assuming that, let's give an example right here. Assuming that we have some sort of input that we're receiving from our clients, from the users of an application, and that input is at some point parsed as an XML document. Well, the contents of that XML allow you to define an entity that is of type a file on the system. So you might be using this to generate some random values. You might use this to perhaps load some file from the disk, maybe a profile picture, maybe a document that belongs to the user. But a specifically crafted XML document can actually instruct the application that is reading this file to display some sensitive information on the system. For example, the etc password or the etc shadow file, because it's just a location on the disk, basically. If you're asking for a file on the disk, make sure you're extremely careful when you're sanitizing the input that references that file. It's extremely easy for an attacker to craft a specific request that is going to request another file from your system, one that you have no intention of publishing to your clients, to your web application clients. Next up on the list is the directory traversal attack, or the path traversal attack, also known as the .. attack. And it's based on the fact that whenever a certain web application embeds a file location in its URL in a post or GET request over HTTP, well, that file location has to be thoroughly sanitized, because if, for example, the application is designed to display a specific image or a specific file that belongs to the logged in user, and that file is referenced in the URL, nobody's stopping you from trying to reference a different file in that URL, including system files. Let me show you an example of this. So the OWASP community is a great place to document and to thoroughly understand all of these attack types. That's why I'm using it for a couple of these examples here. So path traversal, let's scroll down right here. I'm going to see an example of an application that is located at somesite.com and then includes a location for some file on the disk. File equals report PDF, home equals index HTML, and so on. So in these examples, it's possible to insert a malicious string as a parameter instead of these valid files right here to access files located outside of the application's directory. So potentially we could do something like this, right? So instead of somesite.com get files JSP file equals something, we could do it like file equals go one level up, go one level up, go one level up, one level up, until we actually reach the desired location. For example, etc shadow or etc password or other system file that we might trick the web application into displaying to us. Now, directory traversal is also easy to detect because the characters required to navigate in the file system are pretty easy to spot. Now, we also have to take into consideration that these characters might actually be hidden behind % encoding. or even double encoding or triple encoding, or how many times you want to perform that encoding in order to obfuscate your real intentions. Right? So make sure that whenever you're looking for directed traversal proof, you're not just looking for dots and slashes, but you're also looking for potential percent encodings that might indicate that there's a hidden path in there. And of course, in case you're wondering, one great way of mitigating this is ensuring that the application doesn't have permissions to display all those system files. So don't run your web applications with root privileges, don't allow them read access outside of their own sandbox, outside of the files that they're supposed to deliver as web application. Don't let them roam free all over the machine that's hosting them. Finally, the last example here on our list of shame is server-side request forgery, in which the attacker tricks a server, a web server, into executing additional code on his behalf, especially in situations where the server is just a front end and there's a bunch of other third-party services, including cloud services or backends or middleware behind it. Now, communication between the front end and all the servers that it depends on in the back end, that might not be so secure, or it might be based on some sort of an implicit trust. So using specially crafted requests, potentially an attacker could instruct that web server to execute some other requests and reach those other services behind it on the attacker's behalf. For example, an attacker might be sending crafted HTTP requests that hide within them, in their headers, a second HTTP request. And if specifically crafted for that web server, the web server might be tricked into executing the second HTTP request and thus accessing some subsequent dependent services that are only available internally on the attacker's behalf. That way, the attacker might be able to execute code or push some requests to services that they would normally not have access to. And this is one of the attacks that are specific to cloud environments as well. For example, you can see this on the OS website as well. Cloud services such as AWS do provide a REST interface, an API interface, which is accessible here. This is normally an IP address that cannot be accessed outside of the local host. Now, this stores configuration details, and sometimes even authentication keys can be extracted from this location. So if you can trick a virtual machine that is running in AWS that is publicly facing into querying this location right here and displaying that result back to you, that's a type of server-side request forgery. Now, I know this was a lot of content in a very short time span, but I really hope that I managed to explain this as simple as possible. There's a lot more to discuss about these web attacks. There's an entire industry about defending and developing attacks against web applications. But for Security Plus, this should be enough. So thank you so much for watching. See you on the next video. Don't forget to like and subscribe. Bye-bye.